Good morning. This is Mr. Sala, and today I'm going to run through the notes that I issued you yesterday that you should continue to run through and fill in today. So we're moving into motion now, and in physics, motion is often referred to as mechanics. And for these set of notes, the part of mechanics we're going to be dealing with is called kinematics, and that is motion in one dimension. So going from point A to point B in one dimensional path. When we move on to the next unit, we'll be working with forces. So that type of motion would be referred to as dynamics, and that would be occurring in multiple dimensions. Right, so these terms are important. They may come back as part of some vocabulary matching on your next quiz. So please note that, and there is some other vocabulary throughout this note packet that I will point out also. All right, so again, these notes are pretty straightforward. Can see they're guided. You just are filling in the missing term or terms as you go through. And I did notice a few students did finish yesterday, so then they chose when they were going through the examples to using the pen and Kami to complete that, which is obviously the best way to do it. And again, today we will also be having a Google Meet at noon where I would encourage all physics students to at least check in, and I can answer any questions you might have as you make your way through the notes. All right, so we're talking about motion. So something is moving from A to B over time, and we refer to that as speed. And again, we know speed in terms of driving in a car, or you're talking about miles per hour. Maybe we've heard about some barriers being broken, right? The speed of sound, which is, actually breaks out through the metric system as 340 meters per second. And you can convert that back into miles per hour to, find out exactly what the speed of sound would be um, in miles per hour. Again, something we understand because this really has no meaning to us because we're used to the miles per hour. Four types of speed. So again, you're going to have average speed. And again, this is where you want to look at and distinguish between these because this is just regular vocabulary. So you're looking at a total distance divided by the total time. So that would be your average speed. Your instantaneous speed would be your speed at any specific point in a journey. And again, policemen can use a radar gun to determine your exact speed at an instant. Um, Back before radar guns, if they were to have obtained your speed, they really would have been using the average speed because they would have taken your speed from a point to a point and divided it by a time. But now, through technology, they can use a radar gun to get it at a single point. The third type of speed would be changing speed. So this is going to describe the motion during a journey where your rate will vary. So again, speeding up or slowing down. And then constant speed just means that you get out to, a certain speed. You get on the highway, you get up to 55 miles per hour. You set the car on cruise control and it just stays 55 for however long you choose. So cruise control, or again, a certain speed on a treadmill. So 4 different speeds: average, instantaneous, changing, and constant. Again, a lot of that just had to do with vocabulary, and you would want to distinguish between the 4. So how can you calculate? Again, speed is simply a position that occurs over time. So it's a distance divided by time, and interchangeably in physics, and we'll get into the difference in a minute, a lot of times we refer to it by the term velocity. But really, again, it's just a distance over a time. And this is the triangle that we will be using quite a bit throughout physics. Some of our formulas are a little bit more complicated, but for quite a few, we have that magic triangle. So again, you had your velocity equals your distance divided by time. You set it up like this in your notes or when you're working through problems, then it's very easy to see. If you were to cover the V with your hand, you could see that you would have distance divided by time. If you were given information and you had to cover that you needed to, say, find the distance, then you would take your hand and cover up the D, and then this now would become, you would take your velocity and multiply it by time. And then again, if you were finding time, cover the T, and then you would have your distance divided by your velocity. So an easy method to learn, to put in, and then to use as you're solving each of the different parts to find speed. These are really good. This is just really good advice here to follow when you're trying to solve any problem in physics. Again, check your units and convert as necessary. So again, if you're given something in kilometers, you're going to need to convert that to meters. If you're given a problem with hours, you got to convert that to seconds. You're going to start, as we continue, I'll be a little lenient here in the beginning, but we're going to look to always solve into our correct number of significant digits. Sketching is always important, just to visually set it up and realize what's going on in the problem. Looking at all the variables involved. Obviously, this first packet, we're going to be dealing with one formula, but as we get going, you're going to have to make your choice between a few different type of formulas. Then you solve your problem after you've gone through all this, and then again, check your units and your sig figs. Then you need to check to see whether or not you're being asked your answer is a vector or a scalar. We're going to define that in just a minute here. Right, so simply enough, when you attack these problems, I know you most likely just going through the motion in your notes, but really there's a lot of information here. So a dog runs 25 meters in 15 seconds. What is the speed? So 25 meters, you know, is a distance. So you write it out. When I ask you to do the problems, I do not care how simple they are. Right now, you still need to write out these steps. So you know your time is in 15 seconds. And then what is the dog's speed? So we know we're looking for velocity, and we know that is going to wind up being in meters per second. And then you just come on over to your triangle, which you know is velocity equals your distance over your time. And then you divide and you would get your answer. 1.7 meters per second. Right? But really the point is that when I ask you to show work, you need to show me that. You should have your triangle somewhere set up so you can really just cover it and choose which one of the three formulas you're solving for. And then you plug in your numbers and you make your calculation. And again, this would be correct. I don't, if there was running numbers here, because there's only two sig figs in the problem, you'd have to limit your answer to those two sig figs. All right, and then you have some more examples going through that you should calculate. Mixed units, again, converting from hours to seconds into, that's where the dimensional analysis comes in. And when does direction matter? This was what I was referring to previously about velocity being a vector. So a scalar will have magnitude. Again, with science, we get caught up in terms, and all this means is the size. So have a size and a unit, but they do not indicate direction. So in that first problem we didn't worry about what direction the dog was going in. But if you're talking about a vector quantity, they're going to have magnitude and direction. Right? So the dog traveled 1.7 meters north. So you're including a direction, so that now becomes a vector quantity. And we'll get some more information about the difference between scalars and vectors as we continue. Distance versus displacement. Again, looking at distance is just a scalar. It's just you went from point A to point B. Displacement now is the difference in position from start to finish, and it's going to include a directional component. Okay, so why does the direction matter? So you're going to consider the following question. Shelby runs 2 miles north and then 4 miles south. Determine the distance she traveled and her final displacement. So again, you're going to calculate the distance so you can add up the 2 miles in the one direction, the 4 miles in the other. So you have a total distance of 6 miles. That's pretty straightforward. 2 miles north and 4 miles south. But then let's look at the displacement. The first step is to set up again using sketching so you understand exactly what is going on. So if we look here, which is the best vector direction to represent the displacement? So you started at a point, you went 2 miles north, and you changed direction. And you came back another 2 and then went another 2 miles south. So really the three rules to adding vectors are vectors in the same direction can be added together, so you keep them in the same direction. Vectors in the opposite direction can be subtracted. And vectors that are at right triangles can be added using the Pythagorean theorem, and we'll get there down the roads in a little bit. So really the correct answer when you're talking about displacement is 2 miles, and technically it would be 2 miles south. So the distance might have been 6 miles, but the displacement was 2 miles. Right here, this is your displacement. It's your total mile traveled from the origin and heading in a specific direction. So you want to get it straight in your mind that there is a difference between speed is a scalar, velocity is a vector. distance is a scalar, displacement is a vector, and it's just because of the directional component. And you continue to run through the notes and fill those in. And then we'll have, I'll just leave any other further questions you have for the Google Meet that we will have today at 12 p.m. So please join me then, and with any questions about the notes or any questions on the contents of the notes, and I will see you then. Thank you. Bye.